Recently, we visited a concrete batch plant to see how they make concrete and load it into trucks.
Not long after, we saw the super passionate concrete guy on TV.
I love concrete.
It turns out he is an Okie, and he teaches and researches concrete at Oklahoma State University.
So we got in touch, and he invited us to his lab so we could see some of the things that he works on. Meet Dr. Tyler Lay. He is a civil engineering professor, self-described concrete freak,
And a YouTuber too.
My name is Tyler Lay. I'm a concrete maniac, and I want to help you make the best concrete you possibly can.
We will put a link to his channel in the description. He covers all things concrete, from the basics to advanced topics and cutting-edge concrete technology. His lab is on the Oklahoma State University campus, and he was kind enough to spend some time with us so we could see the type of research and innovation he does. Concrete has been around for thousands of years, and modern concrete made with Portland cement has been around for 200 years. So you may be thinking, it's well researched, and we know all there is to know about it.
After all, it is the number 2 commodity used throughout the world.
But Dr. Lay says we have just scratched the surface of this important material, and he is dedicated to making it stronger, cheaper, more efficient, more sustainable, and easier to use. Let's check out some of his work, starting with one of his newest projects,
The BAM!
The box auger method printer. Let's say BAM, right?
BAM!
That's the kind of printer it is, all right? So you take concrete and you dump it in here. You see that? That's called an auger. It's a screw. And as it spins, it spits concrete out here. And the way it works is you put rebar, you pour a foundation, you have rebar coming up. Okay, can you imagine rebar coming up out of the ground? Can you imagine it? Maybe? Maybe. So imagine a rod coming out of the ground straight up.
Yeah, that's weird.
Pretty crazy, right? Yep. And imagine a whole line of it. And what the BAM does is it takes that line of rebar and it puts concrete around it. It puts concrete, it smooths it, makes it look beautiful, comes right out like a cube, right out of the back. This is a 3D printer. The cool thing about this is that this thing hooks up to a skid steer, like a tractor. And those are everywhere. Some 3D printers are specialized. That means they have to have a very special piece of equipment to run it. This, you can run it with anything. So my thing is that if you can rent one of these, then you can print a house.
Maybe. Yeah, maybe.
We'll show you one later on that we printed.
This is a small demonstration of the rebar wall before it's covered with concrete. And these are the first building walls built by the BAM. These walls went up in just 14 hours and only required 3 people. It was completed at a fraction of the cost of traditional construction, and the final result is stronger with a longer lifespan, resistant to tornadoes, rot, insects, and other damage. These walls will be around a long time.
Because you said 8 inches.
8 inches by 8 inches. That's what these are. This one was 16 by 8.
And y'all just decided to push it to see how far.
So we can do 16, but the mix has to be right on. Okay. Mix has to be right on.
Cheaper, faster, and better already, this construction method will only improve as it gets refined. Back in the lab, Dr. Lay explained how they measure the air content of concrete and why it's important. It starts by taking a slice of concrete and coloring in all of the aggregate black.
And then there's small black things that are sand, okay? And then every white dot is an air bubble. So what we do is we cut this, polish it, color it black with magic marker. We put in powder and pound the powder in the holes. Yep. And we come back in with a microscope and color in the rocks, make sure there's no holes in rocks.
From there, an image of the sample is taken and fed into special software that analyzes the number and size of the white air pockets. Dr. Lay says you want about 6% of the concrete volume to be air bubbles.
Too much or too little air is a problem.
You don't have enough bubbles.
Then it's not good for freeze-thaw durability. The reason why we want bubbles is when the concrete gets wet and freezes, that ice forms inside the concrete, and that water has to have a place to go. So it has to escape to a bubble.
Okay.
That's what it's all about.
And then if there's too many, you got voids.
Too many, it's too weak.
And then the bubble size, you want little.
Size matters a lot, and little is important.
These freezers play an important role in the lab. Concrete continually cures as it ages. Sometimes they want to test a concrete sample at a specific age, but timing the test to when it was poured is not always possible. When the samples are frozen, their aging process is stopped, meaning the lab can hold the sample at a particular age until it can be tested. These special concrete forms allow a strain gauge to be embedded in the concrete. Wires connect the strain gauge to a computer monitoring system so that the internal forces can be continuously measured as the sample cures and acclimates to different weather conditions. Of course, the actual weather cannot be controlled, so the lab uses special weather rooms to simulate different weather conditions in a controlled way.
Desert! Come on in.
Really is humid.
It does feel a little humid. I'm actually going to check the controls on the room and make sure that it's what it's supposed to be. It does feel a little bit more humid than it should be. But this is the drying room. So, do you remember that beam I showed you out there with that gauge inside of it? Remember that little barbell was inside of it I was talking about? That's where these go, here. So this room dries them, and as they dry them, the concrete shrinks. This concrete is like a hard sponge. A hard sponge, like a rock.
Yeah.
And it moves when you pull water out of it. Pretty crazy, right?
Yeah.
So that gauge, which is on the inside, if we had x-ray vision, we can see inside and see the gauge. That gauge moves as it dries.
And all these gauges are hooked up to a computer, so you're monitoring it the whole time.
Constantly.
And how long will you do it for?
As long as they'll pay us.
Okay.
About 90 days.
About 90 days is when it roughly puts.
That's kind of when it kind of like tapers off. For this size member, that's kind of where it tapers off. You hear that noise? Listen. What's it sound like? What's it sound like? Maybe a shower?
It is a shower.
So where it's raining. It rains inside that room all the time. It's a fog room. Yep. So we store our samples. It's 73 degrees Fahrenheit, 100% relative humidity. It rains 365 days out of the year.
Wait, is that where the rain comes from?
That's like a rain control there. It spits the rain out in all different directions. Pretty crazy.
Yeah, I actually.
Big environmental chamber. So we'll put it up here. Come feel this. Ooh, you feel the heat coming off that? Yeah? So we're using it to dry stuff right now. Only to dry stuff, because one of our other ovens is actually broken. But with this, I can make it rain, I can make it freeze, I can make it hot, I can make it cold, I don't have it, but I can buy things. I can even make the sunshine inside with certain lights, anything I want inside this chamber. So I can simulate any weather condition I want inside these chambers, which is pretty cool, right?
Yeah.
That's pretty awesome. And then these, they're not running right now, but this is a freeze thaw box. So we put concrete in here. We're actually calibrating this. That's why all these wires are coming out. We put concrete in here. We fill it full of water, and it freezes and it thaws, and it freezes and it thaws. We shut the door, obviously. freezes and thaws. There's ice everywhere, and then it dries, and then the ice goes away, and then it's ice and goes away again and again and again and again. Crazy, right?
Yeah.
So the way this machine works, come over here, it's not turned on. These are heaters. See these heaters? So they heat in between the blocks. And then underneath this, put your finger underneath this. Down there, that is a cooling plate. So it uses this liquid inside the plate to make it gets really cold. Okay? So it cools and it heats and it cools and it heats again and again and again and again. Pretty crazy, right?
Yeah.
And now, how long does it take to calibrate it? That was your question. Well, it depends. Because if the heater's not working, we got to figure out which one's not working. Then we got to replace it. Or we got to change the voltage to it. That's how much energy or juice is coming to it. And if the plate underneath it, some places get too hot, some places get too cold, and we can put things underneath it.
To test concrete, you need to be able to make it.
So we make it all ourselves.
Wow.
Unless we got to order a big load, then we'll order it. That's where we get all of our concrete. Here, all our sand, rock. We have different sizes of rock. We have big rock, smaller rock, and then even sand. Pretty crazy.
This is the mixing room.
We have our own clock. Oh, the guy that made got that clock would be very excited that you saw it. Okay, he's very proud of his clock. Okay.
Yeah.
So you know, sometimes they have instructions when you're supposed to do something. We follow instructions very, very closely when we make concrete. So they use that clock to time how long they're mixing concrete, so they can make the same concrete again and again and again and again. Make sense?
Yeah.
Yeah. We do all kinds of stuff in here. We bring all of our rock and sand from outside. We actually put it in one of these and spin it, and then we take a sample because we have to know how much water's in the rock and the sand. And we come over here and we weigh out the amount of water we need. And see this big thing? We actually fill it full of water every night. Why? Because we want the water to be the exact same temperature every single time we run the test. Because we got to control everything we possibly can. Does that make sense? We're scientists. We want to make sure it's right. And then we make our concrete over here, store our concrete over here, and then we'll test our concrete out there. That's kind of what this room is all about. Any questions?
No, not exactly.
How about this? What do you think these big elephant trunks are for?
Well, I have absolutely no idea because it has nothing that is next to it.
Right? It's a dust sucker. So when you're making concrete, there's dust. So it will suck the dust off, and we also have a big box up there, and that box up there will move all the air in the room to make sure that it's all healthy for everyone to breathe.
That air filtration.
Yeah?
Yeah.
Cool. And we're trying to make concrete not crack. Right? I mean, no, that's impossible. No. You can do it. And the way we're going to do it is we're going to put in lightweight aggregate. I don't know what that is. You ever been to rock? You ever had a rock that just was very light? Like a rock you could throw at somebody and it didn't hurt them? You ever seen that one of those before?
Yeah.
You ever seen like a pumice stone?
Just a little teeny tiny.
You seen a teeny one?
Toss and
Well,
nobody would feel it.
This one is a big one, but that rock is full of air.
So you can
It's a
just,
volcanic rock.
I see. So
And so on the inside of the rock, you put water. Then you put that water-filled rock in concrete, and then that water comes out of the rock and goes into the concrete over time.
I see.
So it's called internal curing. Internal, and the water does the curing. Pretty crazy, right?
The concrete cylinders you keep seeing are tested for strength by loading them to the point of failure with these machines.
Isn't that crazy?
So they put it in that machine and it keeps putting pressure on until it. Is that normally the way it fails?
Yeah, cone failure. That's what you want.
It's a little fragment. Okay, now it's time to put it back together.
This is an automated compression machine. So all you have to do is put one of these down, you put your cylinder on top of that, you put one of these on top, you close it, you hit a button, it'll sense what size it is, it will load at the fixed rate that it's supposed to until it breaks, and then it tells you the answer. The old school way to do it is to have a human sit here and control this and load this. See this dial up here? This dial moves. They would watch the dial move, and they would move this so it moves at the right rate. And then once it breaks, the red line stays at the very highest that it goes, and you have to read the red line off. Yep, you want to turn it? Wow! You just made it explode!
Yeah. This device uses electrical signals to measure the moisture content of the concrete.
See how these rods are in concrete? We actually send a signal from one rod to the other, and we can measure how much water is between the two rods. What? So we can measure when we make concrete, how concrete dries. And the other thing we do with it is when we make concrete and we put it out in the weather, we can see water going into concrete and water coming out of concrete.
One of their newest additions is a concrete block plant.
So we can make our own block. Like if you want to build a house, you put all the blocks up for the house, right? We're going to relive, the three pigs and the big bad wolf, right? You know what I mean? Where they try to blow it down. So this is a mixer. You put all your material in here and it mixes it up. And then it spits it out into this belt. And then it moves up the belt. And it puts it in this top yellow thing. Come look over here. Puts it in this little funnel at the top. And then it opens and the concrete comes falling out. Well, this moves. This moves out of the way. And there's some holes. See this little plate at the bottom? There's holes there. It spits concrete out. And you have to have a human shove it in the holes. Okay? And then it comes back and goes. And then the whole thing comes up and you get a pallet full of block. A brick.
What?
I know.
So what size are the bricks?
We can make cinder blocks, we can make pavers, we can make all kinds of different things.
Okay, and you said a pallet full. It's not one at a time. This is.
No, you get like 8 or 9 at a time.
If you saw our video on building a house with concrete, you saw this pump, which transferred the concrete from the truck to the special forms. Oklahoma State has its own concrete pump, which gives them the ability to research pumping, like its effect on the air content.
Our own concrete pump. There's only 2 universities in the world that have a concrete pump. One is in Germany, and the other one is right here at Oklahoma State University. Yeah, and we have done a ton of research with this concrete pump, learned so much cool stuff about concrete pumping and concrete and how it affects concrete. It used to be where the block plant is, over there. We used to have a big concrete roller coaster. What? A pipe that would go around, down, up, down, round, down, like a roller coaster, like a baby roller coaster that goes around. It's kind of what this pipe was like. We filled it full of concrete and pump it around, learned all kinds of stuff.
The lab is also a teaching space for university students and for others, like the Oklahoma Department of Transportation.
Oklahoma Department of Transportation Training Center. So people that test all the concrete, steel, asphalt, and rocks, soil, on all of our transportation projects, highway projects, they have to come here once every 3 years to get trained. So we train them on the right way to do the testing, and then we take them back here and we actually watch them do the test. You gonna come see the area?
Yeah.
Come see it.
Also, I did first think this was a lunchroom.
It looks like a lunchroom, doesn't it?
Yeah.
It's like a classroom.
Yeah, I mean, like, look right there.
The continuing education and evaluation of inspectors helps keep our infrastructure, like bridges, safe by monitoring that they are constructed properly. The lab capabilities make lots of incredible research possible, but being able to field test fresh concrete before it is poured is incredibly valuable too. Dr. Lay has developed a couple of field testing devices to do just that. The Super Air Meter can measure the air content and bubble size of fresh concrete in the field. It's a quick and easy to run test. And the Phoenix measures the water to cement ratio, which is a critical factor in both the strength and permeability of the concrete. But until now, there hasn't been a way to measure it. Both of these tools can help determine if the concrete is in spec before it's poured. That is valuable information because no one wants the cost or delay of busting out concrete and having to repour it. We will put links to more information about these tools in the description. Dr. Lay isn't the only professor that uses the lab. This area is being used in some bridge research by one of his colleagues. And other materials are tested at the lab too, like railroad rails and asphalt. We saw a lot of other things, too many to include them all here, and new research projects are getting added all the time.
So if you are interested in concrete and construction, visit Dr. Lay's channel and subscribe.
If you follow his videos, you will see the latest in his research as well as other concrete technology and topics. Plus, you will get his expert explanation delivered in his first-rate teaching style.
Dr. Lay, thank you for showing us your lab and teaching us more about concrete. I hope to visit your lab again, maybe someday as one of your students. To everyone else, thanks for watching and see you on our next adventure.